maybe about 1.5 weeks before, and then you have the final exam on March 18. We have a few chapters left, so I have just uploaded all the content from after the midterm. But I would like to remind you that when you come for the final exam, everything from beginning until the end is included. So whatever you have learned until now, parts of those will still be in the exam. The final exam is a little longer, it's 3 hour exam. The midterm was 2 hours. For the final exam, you will get 3 hours from the system. I've finished checking your exam papers. This weekend, I'll do a double check to make sure that all the marking is okay. And you can expect to receive your midterm scores within next Tuesday, which is 1 week from now. I have opened up my screen to show chapter 12, power amplifiers. I mentioned about it briefly before our midterm exam, but we can start again. On average, the topics after the midterm are shorter. So you can be done for one topic within three sessions or 2.5 sessions. You have learned about some amplifiers earlier in the course, namely bipolar junction transistor and JFET. Those amplifiers, we consider them small signal amplifier. The main areas of concern are amplification, linearity of operation, so linear behavior in terms of input and output, and also the gain, how much voltage you can gain or how much current you can gain. In this chapter, we talk about a different type of amplifier. These are known as large signal amplifiers. The other name for this one is power amplifier, because these ones, they are able to handle much larger voltage signals and they operate at a higher current level. What happens when your device is handling large voltage and current? There's a lot of power dissipation. You have to think about input power and output power. You have to calculate the efficiency. So efficiency is the primary area of concern. Also, maximum power capability. These type of amplifiers should be built such that it can handle large amount of power without breaking down. Impedance matching is another area of concern. If you have multi-stage amplifier between input and output from one stage to the other, impedance matching should be done properly. We do not go deep into the impedance matching in this course, but it is one of the reasons for having large signal amplifier. I talked about five main types of power amplifier. They are classified using an English alphabet lettering system. The first type is called class A. In this amplifier, if you provide an input, for example, a sine wave or a square wave, whatever, the output will show a waveform for the full 360-degree of the input. Means it outputs the full conduction cycle. The operating point, the Q point, is set just near the middle of the load line. You know what a load line is, especially for the amplifier. We studied with common emitter, and the output equation sets the load line at two extremes. One is saturation, the other one is cutoff. Then you have class B amplifier. If you take one piece of class B amplifier and you look at the input versus output, it provides output only for half of the input cycle, 180 degree. which means if you want a full output waveform, you need to combine two of these. That's why it says each amplifier is 180 degree. It implies that there are two of class B amplifiers operating in a pair. The Q point for each piece of amplifier transistor is set at the cutoff point. Where is the cutoff point? You have y-axis for current, x-axis for voltage. Where is the cutoff point? VCE, that's the cutoff point. I think VCE equals VCC when the current is 0, that's the cutoff point. You should remember this. Class AB is the third type. It is a bit of compromise between A and B. It conducts more than 180 degree in the output cycle. When you look at the waveform, the output goes for more than 180 degree, but less than 360 degree. The Q point will be in the middle of midpoint and cutoff, midpoint of class A and cutoff of class B. So it is in the lower portion. We can see some diagrams later on. There's a fourth type, class C. If you leave it alone by itself, it conducts for less than 180 degree of the input. Q point is in the negative axis of Y below the cutoff level. But if you pair the class C amplifier with the tuned circuit, which we'll also study later on, and then the frequency of this amplifier is matching the frequency of the tuned circuit, it can conduct for full 360. For this reason, it is used mostly in radio communication devices for class C. And finally, class D is an amplifier that is used specially for digital signals, digital high, digital low. So it's looking like a pulse. Here is the output of a class A amplifier. You see it's V out over T, voltage versus time graph. The 0 point is located, I go to full screen mode. The 0 point is right here. The amplifier output is for full cycle, full 360 degree. And then there's an average DC level associated with that, which we'll also study. If you look at the IC versus VCE graph, where is the Q point? It's exactly in the middle of the load line. So around the Q point, the input and output, they can swing. The output can swing to a certain extent in one direction and swing to a certain extent in other direction. It has, when you set the Q point in the middle, it has a lot of room to swing. That's why you have a full 360 degree output swing. This one is diagram, output voltage diagram for class B. As you can see, the output voltage is only 1/2 of the cycle. At the other half, it does not output anything. You don't want a device that is on, off, on, off. You want it to be continuously on. So you need another class B amplifier to work as a pair. In 1/2 cycle, you turn on the first one. On the second half cycle, you turn on the second one. Where is the Q point? Right here at the cutoff VCE. Means you have swing only from this point. You can swing in only one direction, the other direction not. That's why you have 1/2 of the peak. It says on the slide, because the Q point is at 0 volt, it should not say 0 volt. What is it saying? It should say 0 current. It's not 0 volt. 0 volt is right here. It's at the cutoff point. That's why AC signal can only swing for one half cycle. For class AB amplifier, compromise between class A and class B, you see the Q point is not in the middle. The midpoint is where I'm putting my mouse cursor. From the midpoint of class A and the Q point of class A and Q point of class B, if you take the middle of these two, you get the operating Q point of class AB. You have more room to swing in this direction, but a bit less room to swing in the other direction. Therefore, the output conduction will be more than 180 degrees of the input cycle, but it will not be exactly 360. It can be less than that. Here is class C. The Q point is below the cutoff point. Conducts for less than 180 degrees of the input cycle. The table here shows the operating cycle and power efficiency of all these 5 classes. As you start from the lower letter and then go to higher letter, you will see the conduction cycle is decreasing. For example, class A, full output 360 degree. Class AB is between 180 to 360. Class B is 180. The C will be less than 180. D is not defined as a cycle because it's a pulse operation, high or low. Also, there's a footnote. Class C is not usually used for large amount of power. In the radio communication circuit, you don't have high voltage and high current like the other one. Efficiency is not given here. It is not usually measured. For power efficiency, it goes the opposite way. If you start with the lower letter, this is the least amount of efficiency. Usually class A is 25%. If you do some trick in the circuit, coupled with the transformer on the output side, you can increase it to 50%. For class B, between 25 and 78.5% possible. That is AB. Class B, you can get 78.5%. D, typically over 90%. What is the efficiency? It is output power divided by input power, and you express in percent, so you multiply this ratio by 100. Usually there will never be more output power than input power. You get a fraction and then you will multiply that by 100 to get the percentage value. What type of device is shown? You have a BJT. What type of BJT is that? In this circuit, it's a BJT symbol. Is it PNP or NPN?
PNP.
It's NPN. Arrow is going away. What about the configuration? What do you call this configuration? I'm not talking about the bias name. I'm talking about the configuration. What do you call it? Common what? Common emitter. Emitter is ground. It is common to the input base and it is common to the output collector. Okay, what about the bias then? What type of bias is this?
Is it fixed?
Fixed bias. You have RB, RC, there is no RE. So then you have a signal, input signal, that's a sine wave and connected with an input capacitor. When you look at this thing, you can't really tell the difference of whether it's a small signal amplifier or a large signal power amplifier. There's no special symbol for power amplifier in the course, but the way to tell the difference is it is written next to the symbol of BJT. It's written it's a power transistor. That's one way to look at it. If you happen to hold a power transistor in your hand, the construction of a power transistor should be larger than the construction of a small signal transistor, because they are robust, they are stronger, they should be able to handle large volt and large current. So this series fed class A amplifier looks exactly like a fixed bias common emitter BJT. We can talk about the equation. What is IB? If you look at the input loop, what is the input loop? VCC minus IBRB minus VBE equals 0, KVL. So IB is VCC minus VBE divided by RB. You also know IC equals beta IB. And on the output loop, you have VCC minus ICRC minus VCE equals 0. Hence, VCE will be VCC minus ICRC. That way you can find the DC load line. But then, if we go to the next slide, okay, let me point out to you the DC load line. This is the DC load line that you're looking at. This slanted line is the DC load line. What else is happening? This is your Q point, this is the base current. Assume that this is your IB. We found out IB is here. The load line intersects IB. You have your Q point. You have an ICQ. This is DC. You have VCEQ also from DC. But when you provide an input signal, the input signal will swing. We are in the class A amplifier. So if you draw a 45-degree line from here, slanted line, just make it 90 degree. With the load line, you make it 90 degrees. So it's 45-degree angle from the base current. There will be a swing, maximum swing. There will be a minimum swing. In the maximum swing, if you correspond to the y-axis, you have a maximum IC. IC max, you have a minimum IC. We will see the way to find out. It's not from here. We have to find a way to find out where is the upper limit, which we will do through one of the examples in the class. And then correspondingly from that point, if you draw vertically, you will find VCE max and VCE min. We need the max min values of IC and VCE in order to put it in a formula. So here you have a small input signal. The output voltage can swing and the current can also swing. It should not go more than VCE and it should not go more than the saturation current, VCC over RC. That's the maximum level. There's an example, example 12.4. It's a very important example in the book. It shows step-by-step analysis. For a series-fed class A amplifier, we have some formulas. These formulas are provided in the formula sheet in the final exam. So what is the input power? The power into the amplifier, it will come from DC supply. And the input power is always expressed in DC. That's why you say PI DC. It is given by VCC times ICQ. ICQ is determined during the DC analysis. VCC is your DC bias voltage. So you get your input power from the DC bias. DC supply. For an output power, the output power is AC power. That's why it says P out AC, given by VC squared or V squared C, which means the voltage at C squared divided by RC. This is in RMS. You can convert this to peak or peak to peak. What is RMS? If you take peak to peak divided by 2√2 for the sine wave, you get the RMS. So it is converted to peak over 2√2. And when you square that, you're going to get V squared. This one should be CE, from C to E. V squared CE over, if you square the 2√2, you get 8. V squared of CE peak to peak over 8 RC. If it's in peak, it will be V squared CE peak divided by 2 RC, because it's only divided by √2 in case of one peak. Then you can calculate the efficiency. This is the Greek symbol eta. It looks like n, small n, but not. One leg is larger. Greek symbol percent eta or percent efficiency is output over input. Here is another wrong thing. Printing error. PI is not AC. PI is always DC. Output over input multiply by 100. Please correct this one when you have a chance. After series fed class A amplifier, there is another type you can use. It is called the transformer coupled class A amplifier. Usually, if you do a series fed application, only 25% efficiency. If you couple with the transformer, then the efficiency may be improved, can be improved to about 50%. What's happening here? You have your RB as usual. Instead of the resistor RC, VCC is directly connected with the primary coil of the transformer. The secondary coil is connected with an output load, RL. N1 ratio N2. What is this ratio? It is the number of turns in the primary side, we call N1. And then you have number of turns in the secondary side, we call N2. The relationship of coil versus voltage and coil versus current, I don't know if it's in the slide or not. I think it is in the slide, in one of the future slides. V1 over V2 equals N1 over N2. And I1 over I2 equals N2 over N1. For the current, the numbers will be reciprocal. Here's the transformer action. Look at the voltage ratio. V2 over V1 equals N2 over N1. And then I2 over I1 equals N1 over N2. So you can find the current in the primary and secondary side. You can also find the voltage. The impedance ratio, we call it the ratio of impedance. The ratio of N1 to N2 squared, A squared, we call it the impedance ratio. It is RL prime equals A squared times RL. RL is not the impedance. RL is just the load resistor. However, if you look back into the circuit, you will see a value RL prime, which is RL multiplied by A squared. If you take the cross multiplication in this equation, RL prime is A squared, which is N1 over N2 whole squared, and then multiplied by your load resistor. The value of RL prime is important. It needs to be determined. Why? Reason why. You see the load line, it has a slope. This slope is given by minus 1 over RL prime. It is a minus because it is sloping to the left. to find the slope for DC load line. If you find the Q point, you can draw the DC load line using a slope of -1 over RL prime. If you don't understand what I'm saying now, just wait until we do example 12.4. But before example 12.4, we should do a simple example first. Okay, that's why you need to know RL prime, and then this is how you will solve it. I'm not there yet. I'm just showing you the illustration. In this example also, I found some error. Maybe not this slide or the next slide. In this particular example, where is the base current? The base current is right here. 6 milliamp was IB. RL prime was found using the transformer winding ratio N1 over N2 squared and then multiplied by the load resistor. So from the Q point, the person solving the problem using a slope of -1 over RL prime, he or she drew the load line. All right. But then there will be another information in the problem. The problem will say you have a base current level of, let's say in this problem, if I translate back into an exercise problem, it will say given IB is 6 milliamp and the base current swing of 4 milliamp. Did everyone get that? There are two information is given about base current. One is the level itself. The other one is the base current swing of 4 milliamp or a peak base current of 4 milliamp. What does that mean? Can anyone guess? Can anyone guess what it means to have a swing of 4 milliamp? Anyone? No? Shall I explain it to you then?
Yes, I have no idea at all.
Okay. It's okay. We haven't studied it yet, but there are some of you quite smart. Maybe you have figured it out. The base current IB is here. IB or IBQ. I can write it IBQ because it's the Q point. And then you presumably know RL prime. So this slope M equals -1 over RL prime. R L and prime. This is the slope. From Q point, you just draw this load line. But is the cutoff here? Not necessarily. Is the maximum current here? No. It says maximum current swing, peak swing of 4 milliamp means from 6 milliamp, it will go 4 milliamp in the positive direction, which means 6 plus 4, 10, right here. And it will swing in other direction, 6 minus 4, 2 milliamp. That's your endpoint. From endpoint, you project the line here, two endpoints, see, right here. ICQ was just in the middle. So where is the swing? From the middle ICQ, the swing will be, the top swing is here, the bottom is here. IC max, IC min. And then same for VCE. From the two extreme points of swing, drop down on the x-axis. This is your VCEQ, which you found from the Q point. Now this is VCE max, this is VCE min. Why are we taking all this trouble? I'll jump ahead a little bit and show you the formula. We'll do shortly. This is the formula. VCE max minus min and then IC max minus min divided by 8. This is specific to transformer coupled class A amplifier. When you look at the formula sheet in the exam or quiz, There are different formulas for different cases. You have series fed class A, you have series a transformer coupled class A, and then for class B, when we go to class B amplifier, the formula is totally different. Don't try to use one formula with a different type. Your answer will be totally wrong. Now let's try to look at a simple example first while you are looking at this screen. I'll go to your class notebook and find out that problem. In the previous semester, I did example 12.1, which means it should still be there, saved. I just need to bring it to your part. Okay. Power amp. Huh. Example 12.1. Let me copy and paste that, and we will switch our screen in a few moments. It is taking some time to load. Move, copy. Okay. And we will go to collaboration space. Call it power amplifier, and then let me switch the screen for you. So this is an example in the textbook. Calculate, do you see my screen? Calculate input power, output power, efficiency of the amplifier circuit in the figure, and the figure has just loaded. Look what it says. For an input voltage that results in a base current of 10 milliampere peak. It does not say 10 milliampere base current. It says peak of 10 milliampere. How do we solve the problem? Let's have a look. We need PI, P's out, and percent efficiency. What is the formula for PI? VCC times ICQ. In order to find ICQ, you need IBQ. We have the beta value of 25, so ICQ will be beta times IBQ. For the output power, the formula for output power was given as V square CE peak to peak over 8 RC, but we don't need that. We can find how to find that. We can find, instead of peak voltage square, you can use the formula of peak current. So IC peak will be beta times IB peak, right? And then for the output power, you can just say I square RMS times RC, because power is either V square over R or I square times R or V times I. First, let's calculate the IB, everyone. IBQ. What should we write for IBQ? VCC minus VBE divided by 1 kilo ohm. Isn't it? 20 minus 0.7 divided 1K. What do you get? I think I'm gonna change the screen a bit. How do you calculate IBQ? I write just here. IBQ is VCC minus VBE divided by RB. So you have 20 minus 0.7. VBE is 0.7. And RB is 1K. It is 19.3 milliamp. Did everyone get this part?
Yes.
And then we can find, I think the next one is ICQ. It's beta times IBQ, 25 times 19.3 milliamp. My calculator showing 482.5 milliamp. ICQ is 482.5 milliamp, like 482 milliamp, which is 0.48 ampere. Once you find this, what can you do with this formula? Input power PI, which is a DC. What's the formula? VCC ICQ. Class A amplifier is VCC times ICQ. That's why we needed to solve for ICQ. What's the answer? 20 volt times 0.48 ampere. 9.6 watt is the input power. 48 times 2 is 96, so it should be 9.6 watt. Is this one correct?
Yes.
The problem is asking us to find input power, output power, efficiency, so we have one of the three. P out AC. Is V square of CE divided by RC. If you want to calculate VCE, you can do it graphically from here, but you can do direct mathematical. You can say it is I square C RC. You can also that because IC is the output current. IC square. This one has to be in RMS. We don't calculate power in peak or peak to peak. When you measure in the lab equipment is also measuring in RMS. I square times RC. This is the load resistor, output resistor. If you know the peak or peak to peak, you can convert to RMS. Let's say you have peak current. Divide by 2 root 2, you will get IC in RMS. If you have peak to peak current, peak current divided by root 2 and peak to peak divided by 2 root 2. I think I said something wrong. We have a hint here for finding the peak collector current. The base current is 10 milliampere peak. So if you want to find IC peak, IC just one peak, peak equals beta times IB and peak. Is IB peak given? It is given 10 milliampere multiplied by 25, so you have 250 milliampere. 250 milliampere, you can say It depends. You want to keep it as an ampere or milliampere. I can write 0.25 amp. Did you all understand until this part? Is it clear until this part? So if you want...
Yes, I think so.
Okay. Now, what is RMS? It is IC peak divided by root 2, square root of 2. And you have a square term here. So convert RMS to peak and then take the square. And what is RC? Only 20 ohm, okay? We'll use 20. You can use the calculator. 0.25 divided by square root of 2, and then take the square, that is in ampere, multiplied by 20. The answer will be in watts. In my calculator, I got 0.625 watts. Did everyone get this? So you have input 9.6, output is only 0.625 watt. What is the efficiency? Percent. Efficiency will be 0.625. 625. And it was 9.6. Multiply 100. What is the answer? Find the efficiency.
6.5%.
Yes, it's 6.5. It's terrible. It does not reach the maximum value of 50%. It does not even reach 25%. So this is the problem with class A amplifier. The efficiency is quite less. In the next example, which we are about to do, that one is the transformer coupled class A amplifier. By doing the transformer coupling, you can increase the efficiency to some extent, maybe 50% max. We will see that one. I'll quickly bring you back to the lecture slide.
Teacher?
Yes.
The formula that we used to find it, this is the odd one, right?
Which one?
The formula that we find the IDQ.
IBQ?
Yeah.
It is from the input KVL loop, VCC minus VBE divided by RB.
Okay.
It's older one. This is not a special formula. The new formula is for input-output power. Sometimes you have to think, if you don't know VCE square, you see the peak, some peak, you can convert to peak current, peak voltage, etc. In this case, it is easier to convert to peak current, because when you are given the peak base current, multiply by beta, you can get the peak collector current as well. Another example for you is example 12.1. Before we start doing that, we can actually Go to the slide first. I can't find 12.4. Where is it? 6. 7. 8. Something is wrong. No. Okay, I have to go to my copy of the textbook and then we will bring it in here. Okay, let's switch the screen for a moment. And let me look where I have the example 12.4. So in the slide, let's go to the next one. I explained to you the max and min. So you first get your IBQ. And then in the problem, you're given the peak swing. In this case, the peak swing is 4 milliamp. Once you find the Q point, you can draw the load line using minus 1 over RL prime slope. You just extend the line and then you find the peak swing. The two peak swing points, you can find IC max, IC min, and then VCE max, VCE min. The saturation point here is actually at VCC over RL prime. The cutoff point is the secondary voltage of the transformer. When the swing, the maximum and minimum values of IC and VCE, when the difference is larger, the power efficiency will be larger because they are spread further apart. It doesn't seem that the slide is in correct order. This is the example. But before going to the example, we should know the formula. So this is the formula. Closely look. It is the P out equation is not same as series fed class A amplifier. It's totally different. The voltage swing VCE from peak to peak is given by the difference between maximum VCE and minimum. The current swing is maximum current minus the minimum. Output power is VCE max minus VCE minimum times IC max minus IC minimum. These two things you can say delta VCE multiplied by delta IC divided by 8. What about the input power? Why is there no input power equation? The input power is the same. It comes from the DC source. So input power will always be VCC multiplied by ICQ, which we have to find from the load line. Here, VCC multiplied by ICQ is the input power, always from the DC source. What is power dissipated? It is not the output power. It means how much power is lost. PQ is power dissipation. Input power minus output power. So output power will always be less than the input. Whatever you are losing, that is the dissipation as a heat, because the transistor heats up. There's a formula for maximum efficiency. If you know the max minimum values of VCE, you use this formula multiplied by 50. If you see the larger VCE max and lower VCE minimum means the swing is very large, you will get as close as possible to the theoretical 50%. If the difference between the maximum point and minimum point is less, you cannot reach the 50% point. So now I'll backtrack a bit. This is the main problem. Example 12.4. The circuit is given. Calculate the AC power delivered to the 8 ohm speaker for the circuit. The circuit component values result in a DC base current of 6 milliamp. Just look at the information. And the input signal results in a peak base current swing of 4 milliamp. You tell me now, which one is IB and which one is IB peak?
IB is 6
IB
million.
is 6. Yes. IB is 6. IB peak is 4. So 6 plus 4, the upper limit will be 10 milliamp. And the 6 minus 4, the lower will stop at 2 milliamp. First, you have to draw the DC load line. The DC load line is here. The straight line is the DC load line. This one is the AC load line. The slanted one is AC load line. The straight one is DC load line. You have two load lines now. The AC, I explained, it is negative 1 over RL prime slope. Two load lines. Why do we draw the load line at VCEQ equals VCC? You look at this circuit. This point is C. This point is E. There is no resistor RC. If you put a probe here, VCE, it will actually sense directly the voltage VCC. Because of what? The primary coil is actually a resistor. It is a coil that is having a few turns. It can act as a resistor. If we think about the ideal winding resistance of the transformer primary coil, it's just a few ohm. A few ohm, maybe you can approximate to 0 ohm, which is like a short circuit. Therefore, VCE is directly the DC bias VCC. So the load line will be drawn like this. The left hand side is wrong, but here is given VCC 10 volts. Now I should bring you the problem and then we do step by step. But first you draw the DC load line and then you have to find the VCEQ and ICQ calculation or intersection. It needs both mathematical and graphical solution. And then you draw the AC load line from the Q point such that it passes through the Q point. Slope equals negative 1 over RL prime. And then from then everything is done graphically. I cannot use this one. This one is wrong. It does not correspond to the one in the class. But what it says, DC base current of 6 milliamp. So this is your IBQ line. And if VCC is given at 10 volt, you draw a straight line. I'm trying to draw straight. Autocorrect. Very nice. Up to this point is okay. But then these values are wrong. They did not provide the right value. How do you find RL? You need to know N1 over N2. So while you are waiting, I have to open my textbook and bring the actual problem. Just take a screenshot and then bring in the class notebook. I have the circuit. So let me copy the circuit first. Take a snapshot. Copy. And I'll put now in the class notebook. Just give me a few moments, maybe about a minute. I have a snapshot that is being copied. inserting the image. Okay, then I have to copy another snapshot which will give you the correct IC versus VCE graph. So I'll put it on the right hand side. Okay, now I'm ready to switch the screen over. Not this one. Another one. This one, can you see? Can you see the two figures on your screen?
Yes, we can see it.
Okay, maybe it's a bit small for your screen. I'm not quite sure about that. Some information is given. So I'll highlight those information. RL is 8 ohm. N1 over N2 equals 3:1, means the A is 3. A equals 3. What about the impedance RL prime? RL prime, the impedance is seen looking into the primary side. If you look back from the output side, you see RL, but if you look into the input side, this is the input impedance. It is given by A squared times RL. So RL prime is like this. RL prime is how much? What is A square? 3 square is 9. 9 times 8 is 72 ohm. I'm doing a shortcut. I'm not writing the formula. RL prime is 72 ohm. First, what is the first step? Draw. What do you draw? Draw the DC load line. So we have determined that because of the transformer ideal winding resistance, which is a negligible few ohm, VCC equals VCE. They are equal. We'll draw a load line from here. I'm trying to do by hand. It will not look proper. And it does not autocorrect either. See, just a rough idea. We'll draw like this. Okay, I think that's good enough. What was given? The base current IB, 6 milliamp. This is our Q point. Where is our Q point? Right here. 6 milliamp. So I mark it. You have to draw a slope of what? What is the slope? Minus 1 over RL prime, isn't it? That's the slope. If you have the graph paper or pen, pencil, graph paper, you can actually do that. There's another way of doing it using a shortcut, which I'll also tell you. So now you have to draw the AC load line from the Q point. A slope of minus 1 over 72. Do you remember the slope equation from mathematics? What is the slope equation? M equals what? Y2. We'll spend today's class entirely in this problem because it's a big one. Y2 minus Y1 divided by what?
2.
X2 minus X1. You need the coordinates. If you actually take the 6 milliampere base current and then you extend it, this is ICQ, and the value of ICQ can be determined. You know what is it? It is 140 milliamp. In this graph, it is 140 milliamp. MA. This is ICQ. If you are to draw a line from here to here, you can find the slope. From here to here, do you know what is x2, what is x1? x2 is 10. Here is x2, y2. x1 is 0. You don't know y1. You know m, you know y2, x2, x1, you don't know y1. There's only one unknown variable. Let me try to draw the slope. If you try to draw the slope like this, so this is x2, y2, this is x1, y1. You have to equate it like this. Minus 1/72 equals, you have to take the value of y2. It is 140 milliamp, so you have to use 0.140 minus y1 unknown, and then x2 is 10, x1 is 0. You solve for it, you'll get a value. What value you get at that point? I think you're gonna get about 280 or 279 milliamp. So I'm waiting for you also to check my solution. Sometimes I can also make mistake. You get 279 milliamp or 0.279 for y1. Or you get y1 is, it depends on how you solve the problem. If you don't take the milliamp, you will get a value of, you should get a value of 279 milliamp actually.
Yes, 279 milliamp.
So 279, I don't know how to zoom this screen. This is 250, 275, 279 is about here. Let me mark this with the red. Somewhere along here. This is 75, 79, maybe around here. It's not accurate. What will you do now? You found the other y point. You all know the other points. So you can draw a straight line. This kind of thing is possible when you have a written exam. I used to ask this one time. I gave all the graph paper and everything, and I asked the student to solve. They can do it in the in-class exam. And then, you know, if you extend further the straight line, it is not, see, it's not going well. So now you extend, you have a straight line. Then what you have to do next, it is given peak of 4 milliamp due to the input signal. So 6 milliamp plus 4 is 10 milliamp. You have to stop right here. I'm going to put the stop point here, right here. It will not go all the way to the top. This is IC max. IC max. And then, do I go all the way here? No. 6 minus 4 is how much? 2 milliamp. So this will be my, just extend the line. IC minimum, it looks like 25 milliamp. This one to me looks like, I don't know, what should I say, 260 milliamp or 255? And then, do you know how to find VCE max and VCE min? Well, right here. This is where we stop. So VCE max is around 17 volts. VCE minimum we have to draw from this point, the end point. right here. To me, it looks like, from this graph, it looks like around 2 volt or just over 2 volt, or 1.8, 1.9. IC max, it is, let's call it 260. And the minimum IC is, obviously, it is half of 50, it's 25 milliamp. Then you can use the equation P out equals delta VCE and delta IC divided by 8. Let's find the P out. What about P in? The input power. What is the formula input power? You remember PI is VCC times ICQ. Did we find ICQ? You know VCC is 10 volt. What about ICQ? We found it graphically from IBQ. This is IBQ. If you extend horizontally on the IC axis, that is ICQ. So ICQ is around 140 milliamp. You multiply by 10 volt, you have how many watts? 10 volts times 0.140 ampere. Is it 1.4 watts? For P out, let's take the difference. There will be some error because I'm not doing properly. Delta of VCE. Do you understand what is the delta of VCE and delta of ICE? This is multiplied, it's not minus, it's a multiplying dot divided by 8. What is the difference? 17 minus 2, so 15 volts about, and 260 minus 25, because upper current is 260 milliamp, lower current is 25 milliamp. I get about 0.4406, 0.441 watt. According to my drawing, the book is more accurate. So what is the efficiency? Can you calculate the efficiency?
Around 31.5%.
Around 31.5. Now let us bring back the actual solution from the book. I'm gonna take a screenshot. No, that's not correct. There's another way without drawing the slope. There's another way of finding the AC load line. Because for a current swing, IC, you can find VCE divided by RL prime. VCE is 10 volt, RL prime is 72 ohm. So 10 divided by 72 is around 139 milliamp. From ICQ, if you add 139 milliamp, you also get 279 along the x-axis. That is another trick. The VCE equals VCC. So VCC divided by RL prime, there's one peak of IC. Now I'll switch. No, we don't switch the screen. We just copy paste, right? Right here. I'm gonna paste here. So it is pasting. just remember what I wrote. I wrote 17 and I wrote 2. IC max, I wrote 260. IC minimum, I wrote 25. This is what my eye sees. Here is the actual solution, which is from the book example itself. VC max is actually 18.3. So I said 17 because of my drawing is not accurate. VC mean I said 2 volt, it is 1.7, is closer. For IC max, the book got 255, I chose 260. IC minimum, I got 25, exactly 25. If you follow this solution, your output power will be 0.477 watt. I got 0.441. And if you take 0.477 divided by input power and multiply by 100, the efficiency is 34.1. So what is the percentage error? My solution has 7.6% error. Within 10%, but if you draw it properly, you will get as close answer as possible. I was also talking about this point right here. Let me, if I increase, everything will be gone, so I should not do that. Let me point out this point, which we found that when you extend the line, it hits at 279. If you don't want to draw the slope, there's another solution to it. Because the peak IC, you can find from here. VCE over RL prime. VCE equals VCC. So you take 10 and then 72. This is a peak. This is one peak. 10 over 72, how much is it? 0.139 amp. So 139 milliamp. This is one peak, all right? So you have ICQ right here. With 140, you add 139. How much you get? 279. This is the maximum point the line will extend to, that is 279. And then of course you have to use the swing, max and minimum swing of the current, and find out where the endpoint is. This will save you a few minutes. You don't have to do this equation, m equals delta y over delta x. It takes a bit of time. Also, if you don't write, if you write 140, you'll get wrong. It is 140 milliamp, and this is in volt. You have to compare volt versus ampere. Any questions about this one? Are there any questions? This is one of the hardest example problems in the entire course. So if you are frightened to see this, I will not blame you.
I'm gonna take a look again.
Yes, please, everyone, example 12.4 is very important one. But this one tells you all the steps of transformer coupled class A amplifier. That's why I like it, because it shows you so many skills that you can actually gain by solving this problem. Now I'm back to the lecture slide. So this is what we did. We drew the DC load line vertical, and we know the VCEQ and ICQ because IBQ is given 6 milliamp, and then we can draw the AC load line either using the slope y equals mx, or you can use that shortcut and then use the value of base current swing to find the maximum minimum VCE and IC. Once you find all that, you can ignore this one. You can use the AC power, output power formula, and then you know input power is VCC times ICQ. What is the efficiency of this one? I just want to calculate. So VC max was 18.7? In the book solution, how much was it? 18.3. 18.3, and then if I take minus 1.7 divided by 18.3 plus 1.7, multiply that by 50, 41.5. You can get maximum 40. Oh no, you have to do square. Okay, 0.83 square times 50. 34.45. Yes. So maximum efficiency of this one is 34.45. You can play with the value of VCC, everything, and then you can increase the efficiency. I'll just do a quick introduction of Class B amplifier, but we will not do a problem yet. We have plenty of time. In a Class B, this is what happens. You have the input signal, and then you have two Class B amplifiers. So let me write B and then B. You know you don't want just one half cycle. So for the first amplifier, positive half cycle is on, negative half cycle off. For the second one, negative half cycle is on. Once you combine, what you see at the load side, you will see a full 360. In order to get the full AC cycle out of a Class B, you need the two transistors. Here is a mistake again. In this chapter, the publisher has a lot of mistake, which I'll point out later on. Both transistors should be NPN. The only time you use one NPN and the other PNP is where it is called a connection known as quasi-complementary or complementary symmetry. But this one is called push-pull configuration. For a push-pull configuration, both have to be the same type, not NPN or PNP. Just show you quickly. Both are NPN, the arrow is pointing out. Isn't it? But if you make one PNP and the other one is NPN, it is called complementary symmetry. We don't study that circuit in this course. So for our next class on Thursday, we'll go into the detail of Class B. I will now call for your attendance. Balam? Is Balam here? Tirawut?
Yes,ครับ
Napatra?
Yes.
Pakon?
Yes.
Rajay?
Yes, Ajahn.
Tonikan?
Yes ค่ะอาจารย์
Michelle?
Yes ค่ะอาจารย์
Phil?
Here, sir.
Silicon?
Yes ค่ะอาจารย์
Visalut? Mr. Visalut not here?
Yes, can you hear me?
Yu Cheng? Yu Cheng? Sheshihan?
Yes อาจารย์
Patampong?
อย่าครับ
Rongsu?
Yes อาจารย์
Martin?
Yes, Ajahn.
Kolawit?
Yes.
Pichayut?
Yes ครับ
Jimma? Oh, Jimma is somewhere. Natalia, raise your hand. Or someone raise hand. Yu Cheng? Okay, Yu Cheng is present. Swanyuan?
Yes.
Satawat?
Yes
Yapeng?
Yes.
Seni?
Yes, present.
Siripok?
Yes.
V2?
Yes, I'm here.
San An?
Yes
Waramet?
Yes.
Nava 1?
Present
Nathapop,
Yes.
Borapat.
Present.
Okay, Miss Nataya is here. Miss Pichaya Pom.
Yes, sir, I'm here.
Pomchan,
Yes, I'm here, sir.
Hiladon,
Yes, Ajahn.
Titsanapong,
I'm here.
Sitya, Tasin, Sukaina.
Yes, teacher.
Is Tasin present?
Yes, teacher.
Sirin,
Yes, teacher.
Min Luinu, Min Luinu absent. See you on Thursday.
Thank you, sir.
Welcome.
Thank you, teacher.
Teacher, Atif person.
Thank you, Ajahn.
Ajahn Council present.
Kongshu is present.
Yes, Ajahn. Thank you, sir.
Okay.